Okay, what I'm going to show you today is split works and electrode works. Split works first. We have a simple part of a inside of a car handle created some years ago. It's a simplified part, and what we want to do is split this part. And the way we're going to do it is by starting off with split part. So with a split part, we're actually able to automatically preview a direction which shows us the core and cavity areas of the part. So you can see now that we're looking at the core and cavity
George,
area.
could you hold on a moment, please? Could you show your screen?
I did. I showed show screen. I did a show screen. Oh, I'll do it again. Press on show screen. No one can see your screen.
Hello, good afternoon, good morning, good evening, wherever you are in the world. Thank you very much for joining this webinar. We will start in approximately 4 minutes from now.
Okay.
Thank you very much for your patience.
Okay, can I start?
Just give her just 2-3 minutes, and Ahmad will introduce you, and then we'll start.
Okay, great. Can you see my screen at least?
That we can, yes.
Partly splitted or partly finished. You can see here that there's the blue areas where I did the explosion beforehand, or exploding the part. You could see these blue areas were actually part of the core, and so that's not a very good thing. It's undercuts. These are undercuts. We'll show how to solve them in a minute. Furthermore, we can also make sure that all the faces in the core are completely added to the core. And as you can see, we've done here. We also have faces which are pointing in both directions. Those are shown as well. This altogether is just a preview, and I can do quite a lot of things in this preview to check all sorts of things. For instance, these faces are showing in both directions, and you can see them over here. I can actually ask to create a silhouette, and when it creates a silhouette, we can see that it breaks them up into the cavity and core faces. But obviously, this can't be exploded in, or it can't be extracted in this direction, because there's a core face in the middle of the cavity area, or cavity face in the middle of the core area, and so that's not a very good solution. And anyway, we're going to have to make side cores. So I'm going to delete those silhouettes or those cutting areas and go back to what I had before, and I'm going to use these faces afterwards for side cores. Another thing is that at this stage, in fact, we can change the direction of the split. So I'm going to change the direction, for instance, by just pointing on a line, and it automatically changes the direction of the split. And you can see now that instead of a closed parting line, I've got some open parting line in the middle, which is shown by this pink line. And I would have to then close it somehow, or fix everything up, change the draft to make that a good angle. But obviously, no one would think of splitting this part in that direction. Just to show you that you can actually choose directions to decide which direction is best for you. Well, as we saw in the initial direction that was chosen, that's the best direction to choose for this part. And so we're going to choose that. And once we've decided by the preview that that's the direction, we now create what we call the SplitWorks environment, which includes folders. You can see under this tab, it includes folders which have both cavity and core folders, as well as both directions, faces in both directions. These aren't copies of the information. It's the same information, just with pointers pointing to the various areas. Now, we have some side cores over here, and we might want to move them. So I'm going to say, okay, let's move them, these faces, and put them into the side core. So we're going to put the first one into side core, and also this one we're going to put again into another side core. So they're in the side core areas. It could be one face and it could be many faces. At the moment, from this simple part, it's just one face. The other thing is, remember that at the beginning we saw that we had these faces over here, which were in both directions, or actually they're undercut because they're cavity core faces within the cavity. So what we can do is edit. I'm going back to working within the SolidCAM environment, and I'm going to edit those bosses that we created there, and we're going to change the draft direction. So we're going to draft outward, and what you'll see is that the software automatically updates to show the new splitting of the parts, so that the faces have become green. They're in the cavity direction because I changed the draft angle, and also those two closed parting lines have disappeared. So everything I do geometrically with this part, everything will be updated. The information I have will be updated, so the split is driven by the geometric limitations, the direction of the faces, in other words. But a lot of times during a mold design, you would like to have control over the mold that you're creating. So what we can do in this case is we can actually use this part over here, this environment, to change things. For instance, I can move this cavity face to the core by just saying move it to the core, and now you can see that it updates. It's in the core direction. Well, I've moved it to the core. It's not in the core direction, but I've moved it. I now have control over my geometry, and you can see also that the parting line has changed. And moving it to the core means it's part of the core, but we haven't lost from where it comes. And you can see here at the bottom, the face that I moved still has where it comes from. So geometrically speaking, it's actually pointing to the cavity, but I've moved it to the core. And as mold designers, you know that you have to often do that kind of work in order to properly create the part or the inserts that you need. Obviously, in this case, it's not a good idea, so I'm going to move it back to the cavity, as you can see here. Now, in fact, most of the work done in SplitWorks, in the environment of SplitWorks, is done to get to this situation and can be done by various tools that we have here. For instance, we can create new groups to move stuff to groups, to separate side cores or new kind of groups. We can hide faces from groups. For instance, we can hide all the group faces for the cavity, and you can actually see inside and where the core faces are. So that's quite a useful tool to find out things that are missing. I'm going to just show them again. You can also do island analysis. Island analysis is to find if there are parts of the core or the cavity faces which are not connected to the other faces. And not only can you ask to do that, but you can also get some kind of you get a little dialogue which allows you to move those faces to another part. At this stage, there aren't any. So, but there's a lot of work you can do in this kind of menu as well. And that's very important for complex parts or for real life parts where you need that. Okay, so once we've actually got to the splitting of the core and cavity, we can then create the surface, and we work on surfaces. So we then create the surface of the core surface, which has been created, and then we request to plug the core surface holes. Now, You can't always plug all the holes, but in this case, we're going to plug them all. Holes which are planar holes, or which are seen to be holes which can be easily plugged using the full surface or using any of the other functionality that we have in SolidCAM. We actually close all the faces, and we have a surface now, and we automatically make this surface knit all these things onto the surface, because we're in the mold industry and we want everything to be knitted into one surface. I'm going to switch off the closed parting lines because we don't need to see them anymore. And now I'm going to create the surfaces around. So I can use any of the functionality that we have to create the surfaces around. For instance, I can radiate, pretty easy to radiate some of these surfaces, which lend themselves to radiate function from the SolidCAM geometry. And I'm going to radiate it out to, let's say, 50 millimeters. Of course, it's just a radiate from the geometrical functionality, so it really doesn't know that we're in a mold design, so it doesn't know that we have to knit these surfaces together. Now, we have a specific function also to create these surfaces. The function we have is a splitworks function called loft. And this loft function allows us to actually take any two either points, vertices, or edge and vertex, it doesn't matter, and move it along an edge. We get a full preview of it. So it's fixed to that edge, and it's continuous with that edge. And we're going to say, keep that function going, because we're going to have to do a lot more than that. So that's the first part. And then we're going to say, okay, on this side, we're going to do from here to here, but of course that's not a good direction. Again, we want to make a reference edge along here. You can also see you can have up to vertex to create the size of the ruled area that we're creating, of the surface that we've extruded. You can also change the distance, you can change the angle, and whatever you want to do. So I'm going to do that as well. And finally, I'm going to make a loft from these two areas over here. So this area over here. So I've created a surface. This is a function where you can very quickly create a surface around the part that you need. And I don't need to carry on doing it after it's finished. And of course, since it's a mold design type of functionality, it will automatically split the part and knit the parts together. Okay, so that's one part that we have. Now, further on, what we want to do is we want to now create the core and cavity from this split part. And that's very easy to do. Actually, we have create solid core and cavity. And what it does is it opens an assembly, a new assembly, puts the surface into the assembly, which we then select, and automatically displays for us the inserts which come from the system actually. These are just boxes. We can create our own boxes and use them so that the information here will be different. And we can use them because we also have here possibility of using external information. Just have to create a box, any type of box or cylinder or whatever you want, or any shape you want, and it will use it for both the top and the bottom. And you can go through that to get to it. You can also move the position of whatever you've created, or from a system that's created. It's automatically sort of done made it the maximum box size it can create on the surface that it sees. And we also have parameters which can be changed. For instance, we're in the core, we can change the thickness, we can make it smaller or bigger in this way. And if you create your own box, or without, let's say without the chamfer, without the radius, or with other things in it, the information, the parameters that you use will all come out over here. So you'll have like an environment, even though of your own, but it will look exactly the same as this environment looks. Now, once you've decided exactly what your core and cavity inserts should look like, and that's fine, you can change them afterwards, of course, because It's all associative. But if that's what you want, then you can create them. And so all we need to do really in order to split apart is to either create a surface on the the core or the cavity, whichever is easier to use. And once you've done that, sorry about that. Once you've done that, you can then explode them, of course. Let's explode them in each way just to see what we've done. So you can see there, this is the core and cavity. Although this is the core and cavity, but remember we still have these side cores, which are reflected by the fact that we have these little things over here, and of course the side cores have to go through this over here, the holes to make because of the fact that it has to be extracted from the sides. So in order to do that, what we're going to do is go into the actual part itself. And now remember that we moved the side cores. We could do it now, but we moved them before to here. So I'm going to take the side core itself and actually do exactly what I did before. And that is I'm going to create a surface the same way as I created the surface for the core. I'm going to create the surface. I'm going to plug the holes for the surface. It automatically hides, at this stage, it automatically hides the part, which is fine. I know that this is the correct information that I need. Afterwards, I'll show the part. And then I'm going to plug the hole. And it plugs the hole. And just to make sure that I've done the right, plugged it in the right hole, I then do that. Now, once we have that, it's a surface created, and you might see a little icon over here of the surface created on our SplitWorks environment. And we now can create side core. So we can create a side core by giving a direction on this, of course, on the surface. And we're going to create a side core, let's say that length. We can also create extensions of the side core, box or cylinder, whatever. In this case, I'm not going to create anything, but just to see that we can create them and create it. So it's going to create that side core. And of course, we have one on the other side, so I'm going to create that one as well. The same way, I'm going to go to side core. I'm going to say create surface. Now, remember the side core could possibly be, and one of the example I'm going to show at the end of this bit about SplitWorks, could be a very complicated part. It could be lots of different surfaces, etc., etc. In this case, this is very simple. It's just one surface, but it could be a lot of surfaces with a lot of faces with a lot of holes, which you have to close as well. So we're going to plug this hole. In this case, when we go to plug the hole, it's actually plugging the wrong side because the holes are the same size. So I don't know which one to do. And I'm just going to make sure that it picks the correct hole. And it's plugged that hole. And of course, as I said before, it's knitted everything together as we expect from a software that's dealing with mold. Next, as before, we're going to go to this side core. I believe it's this one. And create a side core. Okay, to ask for a direction, that's the direction, and we're going to create it that way. So we've created an extra side core. We have two side cores. We'll just show the second side core. And since we've created that side core, let's go back into our insert. This is on the part. We've worked on, up till now, we've been working on the part. We go back to our insert assembly, and it updates with all the information that we've added, plus the fact that those little knobs or the little cylinders that were there have been actually knocked out by these side cores. Of course, we still have a problem where the side cores don't have holes for the side cores, but that's very easily done. You can just edit the for instance, the core, and insert these side cores. Make sure that you actually create a cavity with the side cores. And I'm going to do that by making a cavity with the handle housing, which is already cut from that, and it will automatically cut, as you can see, the holes for those side cores. So in this phase, we've actually finished creating the core cavity and side cores of this very simple part. But in fact, if you look carefully, these aren't real side cores, they belong to the part. And we want them as separate from the part. So we have a function which says take these candidates for side cores, these parts which are used actually as tools to create the side cores, and add them as side cores. And the way we do that is we just go to the SplitWorks and we say add side cores. And so let me just bring this up so we can see it on the whole screen. And so we can press on, we take this part and this part, and we say, okay, they're going to be side cores. So we have to give them, or we should give them names. We don't have to, but we should give them names. So I'm going to call that side core 1. And I'm going to take the second one and I'm going to call it side core 2. Because it has to be saved in the parts. And then I'm going to say add these side cores. And now, if you look at the moment at that tree, you can see there are 3 parts, which is the part and the 2 inserts. It's now going to add the side cores, and it's going to create another 2 parts, each part for the separate side core. Because of course you'd want in your insert assembly all the parts that you're going to put into the mold eventually. So you can see them over here. They've been added to the side core. And of course, any changes to them will not reflect back to the parts. Whereas if you've changed the actual parts inside, it will reflect towards them. So it's associativity in one direction, which is exactly what you want in this case. And just to see that we've successfully done that, let's just let's explode, edit our the feature, the explode feature, and add these. So we can add this one and say, okay, let's move it to there, done. And let's take this one and move it there as well. Okay, so they're separate parts. So we have now separate parts of the complete split entity. We have another function here for those of you in the mold industry, and I suppose most of you are. The important function is sub-inserts. Often with the mold, you have areas which are more delicate, smaller, with all sorts of things which are delicate and which during the mold cycle process might be worn down by the actual creation of the parts. And you would like to be able to swap out and swap in a new part without having to actually create the insert again. So that's a very important function which is often used. And what we're going to do now is we're going to create some sub-inserts, or at least one sub-insert for this part. You'll see in a while that sub-inserts have different ways of creating them. I'm going to create this sub-insert using a sketch, previously defined sketch, or actually not, just sketch which I'm going to define on the fly. So I'm going to take the sketch. I'm not going to dimension it. I don't care at this stage about how big or small it is. And the part that I want to do is, as you can see, is these air holes. I don't know if they're air holes, but these bosses on the top, which create the air holes, I want to make them a sub insert. So what I'm going to do is I'm going to go back into my handle housing, as you can see. Actually, because it's not so interesting, I'm going to hide everything except for the core. So I'm going to show just the core, and you can see here that's the area. And use this function, create sub-insert. Now with create sub-insert, there are many different ways of doing it. I can do it by sketch. I can do it by faces. So I can just pick a few faces. In this case, it's not, there's no faces here which just exactly define that part, but I can connect faces, and I can do it by color. And it could be different areas, and it'll create all the sub-inserts together. At this stage, it's just one sub-insert that I'm creating. So it's by sketch, and the sketch I have to give it. So you can see that's the sub-insert. It's a preview of the sub-insert. And I can add a base to it if I want to, or that base, or a cylindrical base. Doesn't make any sense to make a cylindrical base, so I'm not going to add that. And if I had more than one, I can also change the names and make it a different name if I wanted to. So I'm going to create that sub-insert. And what it's going to do, it's going to make a hole in the core insert because it needs a hole in the core insert. And it's going to create the actual sub-insert. That's the sub-insert that it's creating. and it's created a hole in there as well. I think it's at this stage that I'd like to mention that you can use any of the geometric tools in the SolidCAM environment to fix anything in any of our, actually in any of our modules, and change the information using this. As you've seen, I'm using 90% our SplitWorks routines, but you can also use the geometric functionality here and do whatever you want. And just to show you finally a exploded view of this, so we're going to explode it, collapse for some reason, and explode. Oh wow, I forgot to show everything, sorry about that. So let's show all the parts, might help. So we can see everything. And also this can be now, I can actually add, I can edit this feature and move that sub-insert. I have to just get out, and I can move it just to show you. It's a complete sub-insert, and it's separate from all the parts that we've created. So we have in our tree now all the parts needed, and a sub-insert as well in order to go into the mold. Now, in fact, this is what I've shown you is the scheme of how SplitWorks works and the whole idea of SplitWorks. What I want to show is just one last thing, that since we're working in an environment which is associative, I'm going to take the part itself, open the part, show it. Okay, and I'm going to make some changes to the part, which might be as a result of the fact that it fits with another part, and that part has, they've changed some of the information. I'm sure as you mold designers know that a lot of parts, in fact, all parts that you get to do mold design on them change. They can change twice, 3 times, or 100 times. A very simple mask that you can see on our website, which is for the coronavirus. The one that you see on our website is the first version. There were 17 versions of it, just to give you an idea. The guy had to update the part 17 times, or the part was updated 17 times. So what I'm going to show you is some kind of work that we can do. The first thing we can do is I'm going to edit the sketch that creates these ears, for want of a better word. And instead of, you can see the ears are positioned towards the origin by 40 millimeters. And I'm going to change it to 20 millimeters just to move them across. So I'm moving the ears of the part. And just recalculate. So it's going to recalculate. And you'll notice that when it recalculates, it's also recalculating SplitWorks. It's rebuilding SplitWorks. It doesn't need to, but it is. It's rebuilding everything. And everything's, okay, still the same. Still the same. Here I'm going to take this fillet, and I'm going to change the size of the fillet. And again, you'll see that the SplitWorks, as we showed at the beginning, whenever I work on SolidWorks and in the SplitWorks environment, everything changes together, and information updates automatically. Sometimes it can be a hassle because you don't want it to. You can always switch that off, by the way, just in case you were worried. I'm going to take these, what I called air holes, but I don't actually know why they're there. And I'm going to change them a little bit. So I'm going to move them across here, and I'm going to move them across here. So I've changed them, made them bigger, and everything will hopefully update. So it becomes bigger air holes. And now that I've made these changes of the part itself, if I go back to the assembly, what I can see in the assembly is that everything else has been updated. So if you look, this has been updated. These bosses, or whatever you want to call them, have been updated on the holes. The part's been updated, but the holes as well. You can see they now align completely. So everything's updated correctly. Don't have to do anything more work, even though you have to update. And of course, the fillet as well, we might be able to see it over here, You can see the fillet has also become, it was 10, I think, before. It's now become 6. So basically, that's to show split work, the functionality, and the fact that it's associative with the environment that it's in. It's completely associative. And even if you actually stop working with split works, everything that we've done is still good in the SolidCAM environment afterwards. You can work with it as if it didn't need split works, or you didn't have split works, or you sent this to someone and they didn't have split works. You can work with it as well. Not a problem. And just to show you that SplitWorks is not a software to create just simple things, what I'm going to do is I'm going to save all this, and then I'm going to bring in one of the parts that we created. I mean, this would take 10, 15 minutes, or a little bit longer just to finish it off, but 10, 15 minutes to create by a guy, a mold designer who's well versed with this. So it's a very simple part. But if we're looking at a part which is more complex than that, let's have a look at something we did. It's actually on our website as well, for a company called, doesn't matter. I'm not sure if I'm allowed to say the name of the company. So I'm going to just open this, just close all this information and open this new file, which I prepared. It's this part, just to give you an idea of a real live part, which has been split. And we did the split in less than a day. And you might notice here, one of the interesting things is that the side cores, in this case, are more complicated. You see how big the part is. It's not a simple part. The side cores are more complicated than the basic insert, and the core insert and the cavity insert. You can see the side cores are much more complicated. So it's much more. There's a lot of more work to be done on the side cores than there was on the core and cavity. So just to get an idea of what it's able to do. Okay, I think that that's enough for split works, and we're going to electrode works. So I'm going to just switch off that and open a part for electrode works. So the part that I've using for the electrode works is actually also a part that we split by SplitWorks, and you can see here, I think I can explode it, and you can see the different side, the part and the side core, and the fact that it's been split. But actually, we've already finished SplitWorks, so let's go into let's just open this a little bit more. Okay, so let's go into just the core, just show the core part, because on the core we want to create electrodes. Electrode works is the same as SplitWorks. Actually, it also has an environment where you can run electrode works using the menus from electrode works from the top, which are actually corrupted at the moment. It's not showing them, but all the functionality that electrode works shows also shows on the right-hand mouse button. So what I'm going to do is I'm going to just add an electrode very quickly. Select any electrode that I want to select, a simple one. I have to show which part I want to put the electrode on. It has a direction. The direction can be changed, but that's the default direction. I'm going to say, okay, just add the electrode to this cavity area, or whatever you want to call it, concave area. It automatically finds concave areas and automatically creates the electrode. So that's how easy and quick it is to create an electrode. Not saying that we can't do things which are much more complicated than this, but this is just to show you how easy and quick it is to actually create an electrode. Now, what we want to do with that electrode, a lot of different things. The first thing is we can copy the electrode. We can edit it. We'll show that to you later. We can copy the electrode. So you can actually look at the electrode and say, okay, this is a face. Find me the burn areas which are similar to this burn area on this part. So you can see it's found this area, this area, this area, this area. It's actually looking for this face, checking the area and finding those. And it didn't find me these two, which are in fact the same, but because the faces are different, it's not giving them to me. But I can manually add them. I can say, okay, but I want this one as well, and I want this one as well. So what you see is it actually just one electrode in 6 areas, 6 coordinates. That's all it is. It shows 6 electrodes on the screen, but it's actually just one. So that's one way of going. Other way is to say, well, let's take this electrode and actually add it. I'm going to edit it, and I'm going to add it to different areas as well. The same electrode, okay, through edit. And what I'm going to do is use our seed face to ask it to include this one. And you notice that the electrode has expanded to create a electrode on this side, and the box that I'm using, or the holder, has also expanded. And you know what? I can do it on this one. So instead of having one electrode doing 6, or let's say 4 in this case, 4 areas, instead of having one electrode and just the positions, we can have one electrode doing 4 areas at the same time. And you know what? This area isn't the same, but I can add it as well. Why not? So I've got one electrode doing 5 areas in one go, and I'm going to create it at this moment. So that's how easy it is to create an electrode. It's a special type of electrode, or it's our default type of electrode, which is actually extruding the information. And it's the advantage of using this kind of electrode is the fact that we don't have to, usually, in most cases when using this, we don't have to clean the areas around. But that's not always the case. It's not always possible to do that kind of electrode. For instance, we'll add another electrode, cleaning a different area. Let's change the electrode. You can see that we have here a group of electrodes. Every one with a lock on it means that it's from the system. And if it's not a lock from it, then it's one that we've created on our own, or the customers have created, or customers have asked us to create, and customers can create their own electrodes as well, not a problem. So let's take this electrode, Iroha type of electrode, and instead of exact faces, we're going to use faces electrode. So we're going to actually take this area, approximately this area, We're going to take this approximately this area and say create a electrode around this area. Around is very important. It's not exactly on the area, it's around the area. So I'm going to say calculate the electrode. And what it does is it's going to create an electrode around the area that I've chosen. Let's increase the size of the height of the electrode. So we'll increase the height of the electrode. And there's certain settings, again, these settings are for all electrodes, where you can decide how much around the area you want, how much the Z distance is, how much the bottom clearance is. There are a lot of different information. I'm not going to go into that. And also you can give fillets or chamfers to the electrode itself, which is something often done. And once you've done that, you can create it. So this is a different type of electrode where the extrude actually can't be done, or is not. It's not possible to do it. It's not a good area to do it. And this is such a different type of electrode. And it's obviously not the one you always want to do, because the problem with this electrode is that it has a mess around it. It's all, these faces are all touching, and all you actually want is the middle. So we have functionality, which is to add clearances. And you can actually take a direction. And if you can't see the direction, then you have to just check to see that we have the correct direction. There it is. Take a direction. And what I'm going to do is I'm going to ask to clear these faces. So I'm looking from the top on the faces that I want to clear. And I'm just going closer to make sure I pick all the faces. So I've picked these faces, hopefully. And I'm going to ask to do the clearance. And I'm going to clear it, say, by 10 millimeters. Oh, I used the wrong direction. So I have to clear it by the other direction. That's a little bit better. So I'm carried by 10 millimeters, going through that way, and do it. Now, we're not doing anything outside of the geometric environment that we have. Okay, so obviously I didn't pick all the faces correctly. And I can fix that because I can edit this tangent clearance. See, we have our own little tree here, and we can edit this. Let me just see. I obviously didn't pick the correct faces, I think. Let me just clear the selections and pick them again very quickly. If it works, it works. If it doesn't, it doesn't. But in any event, even if our clearance doesn't work, you can use just the tools that you have in the geometric area to create your own. Okay, let's make it 5. Okay, I don't know. I picked face or something that was wrong at that time. Okay, so we have cleared it, and we show that. So, so we have a tangent clearance, and you can see that I can fix the tangent clearance at any time. And that information, by the way, is within the geometric. So it's in the tree that we have anyway. The different electrodes here, you can see 2 of them. Go back to our environment, and we might want to make, on this same electrode, we might want to make a geometric spark gap. So we can use, for instance, 0.1, just as an example, or 0.2, or point anything. And we've created a geometric spark gap. It picks all the faces automatically. You can add or delete faces. Just to see the result, you have here, you can see here the 3D gap that we have on that. Now, just to show, we've done very simple things, but just to show something a little bit more complicated or a little bit more complex, I'm going to add an electrode just to show just to go a little bit of our more complex or functionality. So in this case, I'm going to take another electrode. I don't know, let's take this one. Okay, so another Eroa one. Okay, by the way, the part and the direction are all modal, so they've stayed the same. I haven't changed, I didn't have to change them. If I use a different part, of course, I need to show it. So oops, that's not what I wanted to do. That's gonna just, that's looking for that cannot, it's actually finding all the faces connected, and that's not what I wanted to do. So I'm gonna clear that selection, because what I wanted to do was pick the faces. So I'm gonna pick them one by one. I'm going to pick each face separately. I didn't want to do them all together. And then I'm going to pick these 2 faces over here. So first of all, I'm picking faces which are separate areas. And the second thing is I'm not picking this boss, because maybe this boss would be created by a core pin or ejector, whatever you want to call it, a core pin, which will create it in the mold itself. So there's no reason why I would have to actually burn that this kind of area over here. I would like to burn this as one part, at least at this stage. And so I'm going to calculate electrode, and it's going to say to me that there are holes in this electrode. Not only does it show me that there are holes in this electrode, but it also shows me where the hole is. This is the hole. Now, of course, it could be a hole as well, which is fantastic, because we wouldn't want to create an electrode with a little part for the hole. So it's going to show me that. And it's going to allow me to do a lot of things. First, I can also say, find all the missing faces. That's one idea. The other thing is I can say, allow the hole. So you're going to have a hole in the electrode, which you might want or might not want. Or you can say, fill the hole. So fill the hole so that the electrode doesn't have this bump in it when you create it. And go that way. So that's a little bit more complex function that I'm doing while creating the electrode. Takes a few seconds longer because it's closing the hole. So hopefully it'll do it properly. Okay, so there we have the electrode, and you can see that it's similar. It's also an extrude type of electrode. It's similar to the others. Of course, there's all sorts of other functionality. We could, for instance, we can take this electrode and we can animate the direction we can animate its movement. And there's, depending on here, there's a 10 millimeter clearance area above. That's why it's doing that. And we can check everything. And there are a lot of things that we can do, which I'm just in this kind of demo, I'm not going to show this. The one thing I do want to show to end with is the drawings, because the drawings are something that everyone wants for electrodes. So we can do each electrode separately as a drawing, or we can do them all together. And when we do them all together, the manufacturing drawing, I can ask to show the holder. And the EDM drawing, I can have either separate for every electrode or separate for every electrode, which is not an instance, or one for all electrodes. Okay, so I'm going to do one for all the electrodes just for fun, because it's nice to see it. And it takes a few seconds, of course. It's creating the drawing on the fly. There's nothing here that's canned. And here you can see it's creating the EDM drawing with one EDM drawing with all 3 electrodes. And of course, the positioning, we didn't go into that, but again, for this short demo, it's good enough. The positioning of the home coordinate system, the positioning of the electrode coordinate system, etc., etc. We have EDM outputs to SODIC, EPX, to can't remember the names, but we have to about 5 or 6 or 7 machines. And if Ingersoll, if someone needs an extra machine, or they have a machine which we don't have an output for, then any customer, then they just have to ask us and we'll create that output for them to add it to our list. I think EPX is the output for Makino. It's a sort of a generalized output. So here you can see the manufacturing drawings being created. And this is the information. I didn't go into how we give different information for different electrodes, but that's the information. Now, these drawings are also customizable, okay? You're able to customize the drawings. I'm just using the defaults for everything, but you're able to customize what you see on the drawing, what views you see on the drawing. Here, look at this. This is a nice one to look at, is the, you can see here, this is the EDM drawing with the 3 electrodes and the positions of the electrodes. Positioning according to each one according to the specific home, but you can even change the home for each one separately. And just one of the manufacturing drawings. That's the least interesting one, but you can have, and when you have these drawings, you can also, this is the default spark gaps and everything else on that, but that can be changed as well. You can have a lot more information that's relevant to. I didn't actually go into the electrode data at all. And I think that is my time, correct?
Yes, George, it was pretty interesting. There were quite a lot of questions. I did answer as much as I could. There was a couple of questions that were asked about the mold design. So I would like to answer that. We have another product called MoldWorks, which you can use to design your mold bases and all other ancillary items inside the mold, including the runners and the other things. And that we could not show because we have a limited time. So we wanted to show something that's very eye-catchy and very important in the entire process. So splitting and electrode are the 2 main items in this. So George, it was very, very interesting. Thank you very much. And there was another question. Raju asked us, how do we put the spark gap? Well, I think, Raju, you missed the explanation. George did explain how the spark gap is added geometrically to the electrode. We put a spark gap of 0.1, and the electrode was created with the spark gap of 0.1. The last one, the blue colored electrode that you see, is basically the electrode which was with the spark gap. You can see there, there's a spark gap of 0.1 millimeter that were put on that. Right. Thank you very much, George. I will make myself the presenter.
Okay.
And
thank you very much.
Thank you very much, George. And I'd like to start the CAM. Sorry. Okay. So I'd like to start with a short presentation. Let me swap. Right. So we're going to take the part that was shown by George, that towards the end, the complex part that was shown at the end. We are going to take that part and we are going to do the CAM also for that. So today I'm going to show you two parts. So quickly, I'll just run through the presentation of what we have today for our agenda. We just saw split works, we saw electrode works, we of course did not see mold works. The mold works basically is meant for designing the mold basis after your splitting is done. So you can take different standards like Futaba, Hasco, DME, the standards all are there inside the product. Like I've shown you the flow of information, we start with a CAD part, which either could be a SolidWorks part, or it could be an imported part like an IGS file or a Parasolid file. From there, we move into SplitWorks. And from SplitWorks, we can have two directions, and these could be simultaneous directions. One could be to move and do the designing in MoldWorks to design the mold. And then we could also do electrode extraction simultaneously, and we could move the inserts into SolidCAM for creating the CAM programs. Remember, there is a one-way associative, which means that if there is a change in the CAD part, the SplitWorks will update itself, MoldWorks will update itself, Electrode Works will update itself, and finally, when everything is updated, SolidCAM will also update all its programs automatically with the changes that have been fired into the system. So that's the flow of the process. What we have today in our agenda for CAM for mold making is basically two items. One is the roughing and the other one is the finishing. In roughing, we have got three different types. We have generic high-speed roughing, then we have a new generation high-speed roughing, and we have Imachining 3D. We are going to see all of these today in our two parts that we will look at. So in our generic high-speed roughing, we have HM roughing, we have contour roughing, we have hatch roughing, we have hybrid rib roughing, especially for electrodes, and we have rest roughing. Whereas in the new generation, we have hatch, contour, and rest. And Imachining, we have directly the 3D Imachining functionality. Once we move into the finishing part, again in finishing we have got generic high-speed finishing, and we have the new generation high-speed finishing. And you can look at the strategies that we support for mold and die making for high-speed machining, like constant Z, hybrid constant Z, helical, horizontal, linear, radial, spiral, morphed, offset, boundary machining, rest machining, contour rest machining, 3D constant step over, pencil milling, parallel pencil milling, corner offset, prismatic part machining, and then we combine constant Z with either linear, horizontal, or constant step over. So we have got tons of strategies to work. We are going to see few of them today because not everything is applicable to the kind of parts that I've taken today. And in the new generation high-speed functionality, we have got constant Z rest finish, linear, constant step over, rest finish, and pencil. So you can have a combination of strategies from generic as well as a new gen to finish up your mold. So we start with Imachining 3D. It's a proven algorithm. It basically saves up to 70% of your time in machining, and even up to 90% when you're machining extremely hard parts, hard materials with very small diameter tools. It's optimized machining for each Z step. That means it goes to one full level first, scoops the material, and then it uses what we call as rest roughing cycle within the Imachining 3D cycle to create step ups that will then create the scallops for us, as you see in the picture below on the left-hand side. The stock is dynamically updated, so it knows precisely where and how much material is remaining. The parameters for cutting are automatically decided by Imachining based on the machine, material, the tool, and the geometry. These 4 items, once we define, SolidCAM calculates everything else for us, including the strategy. And combined with HSM and the new generation finishing strategies, you can call it a complete package for machining 3D parts like dies and molds. We also have SolidCAM HSR and HSM, which is the generic high-speed machining package from SolidCAM. It has very powerful and the finest finishing tool parts available for high-speed machining of complex 3D parts like molds, dies, and tools. Very unique machining strategies and linking strategies for generating high-speed tool parts. Cutting moves and retracts are smoothened and maintain a continuous machining motion. You're going to see that in the part that I'll show today. And the tool paths are very efficient when it comes to machining parts, especially the roughing and rest roughing. The new generation machining from SolidCAM, it's something that was developed only a couple of years back. So it has got the latest architecture, which includes a 64-bit support. The speed of calculations will increase the moment your number of cores in your hardware increase. So if you have got 6 cores, 8 cores, 12 cores, the more number of cores you give to SolidCAM, the faster the calculation becomes. We have seen that for roughing and rest roughing of parts as large as 2 meters on a 12-core machine takes about anywhere between 55 seconds to 1 minute to calculate, with a very small depth of cut, including the holder enabled. Okay, today my system has got only 6 cores, so we are going to see the performance on 6 cores. The calculation is the recalculation. If you have calculated the tool path once and you make a change into it, for example, you change the step over, you change the linking, the recalculation is even more faster than the calculation. So that's the feature of SolidCAM's new generation machining strategies. We also have multi-surface offset. That means you can create infinite number of groups of surfaces and provide different offsets to these groups, so that you could say, for example, in the example that you see, the blue surface will have 1 millimeter offset, and the pink surfaces, which are basically flat surfaces, I've isolated them, I could give 0.2 millimeter offset. So I'll have very less material remaining on the horizontal areas and 1 millimeter remaining in the other areas. So you can create infinite groups like this. Strategies are basically a hatch and contour, so we can do that. And on top of that, we have got the rest roughing, which works either based on updated stock, or it works based on the previous tool, or it could be a combination of both updated stock and previous tool. So you can have 3 types of combinations in calculating updated stock, the rest roughing. The user has the flexibility to define a minimum stock thickness below which it will ignore that area and machine anything above that minimum stock thickness area. So you can imagine that you have got scallops, and most of the times in rest roughing, the tool just goes and rubs on the scallops because it is finding material there. So you can say a value, and you can put a value that is slightly beyond the scallop area, so it will not touch the scallop area at all. It will just go into areas where material is more than what we have specified is remaining. Arc fitting is there, which is for smoother movement when you're doing the rapid movements from one area to the other area. So it makes a pretty smooth movement also when it's doing the rapid. In the finishing, we have again, it's very fast tool path calculations. We generally talk in seconds when we are trying to do calculations with the new generation functions, not the generic. The calculation is even more faster. We have 64-bit architecture even in our finishing. Minimum definition of parameters, hardly 5 to 6 parameters that you need to enter. Rest everything is automatically defined and designed by the software. We have in the new generation constant Z, linear machining, constant step over, rest machining toolpaths that are available. And all of these include a complete gouge check, including the holder. If you have specified the holder, it will take into account the holder geometry also for checking. We also have a part of our mold making bundle, a module called HSS, and this is for machining the surfaces without the need to define any kind of boundaries. You can just pick the surfaces and it will machine the surfaces based on the pattern that you have designed or defined, and you don't need to define any kind of boundaries or anything. And it's a very nice complementary module that goes along with the HSM. It has got advanced gouge control for holder, tool, and arbor, supports standard as well as shape tools, and it's also very useful for machining undercuts. Okay, so it's very, very important. Now, based on all these technologies that we have done quite a lot of trials. Our customers are cutting left, right, and center. So I would like to show you some parts that we did. For example, this part is a mold insert, and the material is a 45 HRC pre-hardened mold steel, and we cut this part on a Makino PS105, and the machining time for this was approximately 240 minutes. The size here is 200 by 160 by 40. Okay, that's the actual part as that has come out from the machine. There's no finishing done, or rather hand finishing done in this case. The same part we moved to a Indian machine, and again it was the same mold insert, pre-hardened mold steel. It was the same block that we took for machining, and this was done on a Jyoti VMC 850. The machining time here was 300 minutes. Okay, because the RPM and other things were not as high as 105 Makino, so we had to cut down on our parameters. So the kind of surface quality that you see is right in front of you that comes out from SolidCAM's mold machining package. We also did another part, which is going to be a part of our demo today. This was done again on a Jyoti VMC 850. Again, a mold insert, a pre-hardened steel, and machining time here was 200 minutes. And the last one that I would like to show you is a forging die that you see on your screen. This again was a pre-hardened mold steel, and this was done on an AMS MCB 450, and machining time here was 400 minutes for cutting this entire part. Right, so let's get into our software and let's see immediately how we machine. So we have this part here. It's a mold insert. It's a pretty, I mean, I can say it's between the small to medium when it comes to the size. It's 180, 135 by 83. Okay, I've put some annotations. I'm going to explain to you why I've put that. So let's quickly start with the machining. I have selected the AMS 450 with a Siemens 828 control on this for machining this particular part. And what I'm going to do is I have stored the entire process from another small insert machining as a process template. And I'm just going to quickly use a process template so that it speeds up my operation. So I'll pick the mold insert process template. You can see all those tool paths that are there as a part of this process. Okay, and I'll just drag it and drop it into my operations tree. Okay, so the template work is over. I'm just going to hide that. So I have my process here, and what I have defined as a part of my machine here is I have defined an AMS MCB 450, and the material used is an impacts bowler. And since I'm going to use iMachining, I've set my level 6, which is a pretty aggressive level because I'm going to use, the machine is pretty new, and I'm going to use a hydraulic vise to clamp this particular part, which I already have here as a part of my assembly because I'm working in the assembly environment. So I have the vise here, and I've clamped this part on the vise itself. Right, so I'll start with my first Imachining toolpath. I'll edit this. Things that are red means the part geometry is not defined, so I'll pick the part geometry here. The tool that I'm going to use is a bullnose. So I'm going to use a 12 corner radius 0.9. So I'm going to make a copy of this 12 0.9, a bullnose, and that's the and it has got 5 flutes. So I'll accept it. Go to the levels. I've picked the level as one of the points on my part, so I've just picked it here. So I can go here to the part here, and I can just pick a point. Okay, so that's it. I'll go to the technology wizard. You can see that the moment I go to the technology wizard, once I've defined the tool, material, machine, and the geometry, my technology wizard has already calculated everything for me. So it's going to take 17mm depth of cut at one go with 3 step downs and an RPM of 2,704 with a feed rate, that's a mean feed rate of 2.1 meters with a radial engagement maximum of 0.6 and minimum of 0.1. Now, what does this define to? Because we have 7.5 kilowatt on the spindle, it's only going to take 1.3 kilowatt for this cut, which is like we are not utilizing the spindle completely. So I would like to change this. So what I will do is instead of level 6, I'll pull it down to level 4, and I'll go here to the turbo mode. The moment I push the turbo mode, you can see that the power requirement jumps up to 7.5 kilowatt. If you ask any machine tool person, how is your spindle life calculated? They will tell you that a spindle life is calculated basically on the load that it always gets. And generally they say we are very comfortable with 60 to 70% of the maximum power that is available as a continuous load. So here we are getting 100%, which is not good. So we need to change certain things. Imachining allows us to override. So I'm going to change my maximum engagement angle and say I'm going to put 30 here. So you can see that when I put 30 or even 35, I get 6.1, so 30 is good enough, where I get 4.5 kilowatt as my spindle power. But just changing the engagement angle here doesn't do anything to the spindle power. The spindle power is affected by these parameters also. You can see dynamically it has readjusted the parameters. The RPM is now jumped to 4,375, a mean feed rate of 4.6 meters, which calculates to about 165 VC and an FZ almost to 0.1. Well, this is good enough for me. I'm going to keep 0.5 millimeter for my next operation, and we'll have 0.1 millimeter as my toolpath tolerance. Save it. I'll hit the calculate button. Okay, that's how it starts calculating it. Okay. Toolpath calculation is done. If you go to the CAM tree view now and ask for the machining time, this machining is going to be approximately 28 minutes. Okay, so which is fair enough for this part. Once this is done, I will now run my new generation rest roughing. So we have kept 0.5, so I'll select my target, and my offset here is 0.5. In my stock, I'm asking it to respect the updated stock and detect only material that is thicker than 0.6, 0.5 millimeter, the previous offset, plus the 0.1 millimeter tolerance that we put. So I said, beyond 0.6, only those areas you work with. I'm going to use a 12R2 tool here. Let's go to the levels. I've detected everything automatically here. Constraint boundaries, I'm using the outer boundary. It's automatically picked up the part outer boundary, so I can click on show, and it shows me the constraint boundary that it has created. Perfect, that's fine. Reference tool, we are not going to give any reference tool because we are going to work with an updated stock of my previous operation. Go to the passes, and my depth of cut is going to be 0.5 millimeter, and my width of cut here is going to be approximately 60% of the flat, or even 70% of the flat. Okay, that should be good enough. That's it. There's nothing else that I will provide except the some changes in the links. We'll save this operation. and hit the calculate button. Now, what I'm going to do is I'm actually not going to calculate this, okay? I'm actually going to put this in a parallel calculation, which means only the stock will be calculated in front of me now, whereas the actual machining will happen in the background, and it will allow me to continue defining my next processes. So it doesn't stop the user. The user only waits for a moment till the updated stock has been calculated and continues defining the operations further. So once the operation starts calculating, I should see a lock symbol. So you can see that the operation has been locked. That means I cannot do anything there. It's being calculated. So I'll just delete this. Once this operation has been calculated, okay, what I will do is I will finish the parting surfaces because they are anyway almost nicely tangential, so I'll not have much material there. I don't unnecessarily need to spend a lot of time doing my work. You can see already in the background, the calculation was done. Okay, so now I will go here and add an HSS operation. I'm going to use a morph between two curves. Remember, I don't need to define any kind of boundaries here. So my drive surfaces is the purple colored surfaces. So I will pick the color from the surface and I'll say find the faces. So it has found all the faces of purple color. And all I need to define now is the start and end edge curve. So I'll pick the start curve, reverse it, continue, 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 pick this, that's it. So that's my first curve. And the next curve is going to be the one inside it. Okay, that's this one. Okay, that's also done. So two curves have been defined. Now I don't want the tool to touch the side here, so I'll give some margins. So I will say start and end at exact with a margin of 2 millimeters on the inner curve. Okay, so I'll go to the tool, pick the tool. I'm going to use a diameter 10 tool here. Select it. Okay, in the toolpath parameters, I'm going to give 0.5 millimeters as my step over. And the gouge check, I'll enable only the tooltip to be checked against the drive surface. That's it. So I have the HSS here. I'll run the calculation. Okay, it's telling me that I've got a pretty high retract feed, which my machine doesn't support. So let me check that. Yeah, change it to 10,000, save it, and let's calculate this operation. This would take approximately 20 seconds, roughly. Okay, that's it. So I've got a pretty nice toolpath here that's going around the part, and we are finishing the outside parting surfaces with this toolpath. Absolutely no retracts. There is one engagement and one retract, one entry and one retract. Right, so we have done that outside, so I know that there is no material left out in the outside. I now like to focus myself on the part area. So I'm again going to apply another turbo or the new generation rest roughing toolpath. And here I'm using an 8 diameter ball nose. Okay. And again, no reference tool, because what I've done here is I'm going to the stock and I'm saying check against respect the stock model. That means we are going to use the updated stock and we are going to machine anything more than 0.6 millimeters. Okay, that's it. I'll save this operation and I will go to calculate in parallel. Again, only the stock will be calculated in front of me and the operation will actually start calculating in the background. Somebody asked a question. I also take questions here. If we can use an STL file, yes, of course, you don't need a solid model. You can actually take an STL file and start machining STL file with our HSM functionality. You don't need any kind of surfaces for that. But if you have surfaces, of course, it's great. Okay, so it's calculated the stock and you can see it has locked the operation for me. Now I'll move ahead and define my finishing operations. Finishing I'm going to do in 3 ways. You see the golden colored surfaces, the brown golden colored surfaces, I'm going to machine them separately. And everything else that is there here, the blue colored surfaces, I'm going to machine using a combination of constant Z and linear. Steep areas I'm going to do with constant Z, and shallow areas I will apply constant Z. Okay, by the time I'm speaking, my machining is also completed with diameter 8. So I'll go to my next operation where I'm actually going to machine these golden colored surfaces. So let me pick the target. The tool is 8 ball nose, and the drive boundaries, I do not want to go and pick them individually. So I'm using the boundary function called selected faces. So I'll say new faces, and let's define the faces. I'll pick from the model this one, and I'll say find faces. Okay, so it has calculated all the faces that are needed. Apply. Okay, and if I say show, you can see that SolidCAM has already calculated the boundaries with respect to the 8 diameter tool that I've defined for these surfaces. That's all I need. In the passes, constraint boundaries is also the same. In the passes, we have a step over and step down of 0.15. So we are using the 3D constant step over. Let's run the calculation. Again, the calculations are pretty quick because the part is not that big. It's already finished the calculation. It's running the links and collecting the toolpath for me. Okay, so you can see that we have made the toolpaths here, taking into account the boundary of that particular diameter. And now we can exclude these regions when we are machining the constant Z and linear. Okay, that's pretty simple. So I'll go to my constant Z operation. I'll edit this back into target. Constraint boundaries automatic, or I can say manually created, because I don't want the operations to go on the other side. So I will select this boundary as my boundary for machining. And in the passes, I'm going to give a depth of cut of 0.2 millimeters, and I'm giving an angle range between 45 degrees to 90 degrees, which will determine which areas are my steep areas. And if you're using a bidirectional, I'm just going to save this operation. I'll not calculate this because I'll also show you the parallel calculations of HSM. Next is the linear. So I will pick the target again. Tool is selected in the constraint boundaries. Again, I will pick the same constraint boundary that I picked for this one, which is contour number 2. So I'll pick contour number 2 as my, go to passes. I'm using a step over of 0.2 millimeters, and we have an angle value of 45. So I'm doing a 45 degree machining, and the angle range I've defined is from 0 to 46. So I have got a degree of overlap between the two tool paths, which is constant Z and linear. I'm going to save this, and then I will go to the next one, which is basically pencil tool paths, because I will have some cusps remaining. I would like to remove those cusps with the same tool. So I'm using an 8 diameter, and in the cusps, I'm going to use a step over of 0.2, and I just want 5 passes in the parallel pencil, or what we call as a multi-pencil. Save that. Since I'm going to have 2 tool paths, one that machine these surfaces in HSS and this main area in HSM, I might have some kind of a small mismatch that could occur because of the different strategies. So I would like to run a common program along the edge. So here I'm using what we call as a boundary offset, where I pick the target and I pick the drive boundary. Simple, I'll just pick the same curve here. This was my drive boundary. Since it is going on the other side, which is basically the anti-clockwise direction, I'll have to define values here. So I go to the constraint boundaries, go to the passes, and since it's gone on the anti-clockwise direction, my right side is 0, and my left side I would like to stay away by -3. Step over is 0.1, that's good enough. I'm also going to save this in the link, it's one way. So save this. And my last one is the rest machining toolpath. Since I've used 8 diameter, I have corners that are much less than 8 diameters. How do we do that? We're simply going to evaluate, click on curvature, and you can see that you can do a curvature analysis. Okay, let's switch off the tool. And I can do a curvature analysis for each of these fillets here. Move your cursor and I get the value. Okay, right, let's switch off. So I'm here, I'm using a 4 diameter tool, and this is how it looks like. Show you the tool. This is how the tool looks like. Okay, that's got a 4 diameter and then the shank of 6 millimeters and then a shrink fit holder. Okay, so I'll select that. And in my reference tool, I have picked my reference tool as 8 diameter. We have another process in the rest machining called as contour rest machining. So in event that your previous tool was a bullnose or a flattened mill, you use the contour rest machining where you can provide any kind of tool as a previous tool and any kind of a tool as your subsequent next tool. It need not be ball nose to ball nose. It could be bull nose to ball nose. It could be flat to bull. It could be bull to flat, whatever you want. Okay, but since I'm going ball to ball, I prefer to use the regular rest machining. And I have got step down and step up, step over of 0.15 at 45-degree threshold. So let me save this. Once I have put everything, I can select all these operations and hit the calculate button. You see what happens. Okay, it starts calculating everything together. Everything, every operation is now being calculated parallelly. So it takes one operation, puts it on one core, one operation on one core, one operation on one core, and then everything is done. It runs the linking, and when every linking is over, it starts collating the information of the toolpath. Okay, the only operation now remaining that is calculated is rest machining. That also has been done. Okay, so you can see it's now displaying all the operations up for me. So we started with the first operation, which was a constant Z operation. You can see I machined only the steep areas here. Okay, but you can see what has happened here. This area is still being machined because I did not exclude this area. This area is being machined, this area is being machined, this area is being machined. So I don't want that. So here comes the next feature of SolidCAM. I will edit this toolpath. Don't have to recalculate anything. I'll go into the boundaries. Okay, and in the boundaries, I'm going to define a new boundary. I'll just pick these areas. 1, yeah. We have 2, yes. We have 3. You can have boundaries in XY direction. You can have boundaries in XZ, YZ, or you could have your own direction through which you can define your boundaries. There is no limitation as to from where the boundaries need to come. I'll provide an offset of 0.5 millimeter here, and I would like to keep the toolpath outside the boundary. Everything else remains the same. Okay, so now it only will run the relinking once again after it has trimmed off the passes. And you can see that I have removed those areas from my toolpath. No more areas are there. So I have edited this toolpath straight away. Right, this is good. The same thing I could also do with my linear machining, but I don't want to do it now. Maybe I can do it later on, or because the whole idea was to show you the feature. My linear machining is also here. And then next is my parallel pencil. You can see that it's just going around the entire area just to clear those cusps that are remaining. No big material removal, just clearing the cusps to give that final nice finish to the toolpath. And then I have the offset. You can see the overlap between that surface and this surface. So I'm creating some kind of a nice merging of those two toolpaths. So I've done the offset machining here and my rest machining. Okay, so you can see in rest machining, I have got the steep area where it is doing constant Z and the shallow area where it is following the fillet. Okay, so I've done even that definition straight away here. Again, I've got problems here, so you can edit these toolpaths with a boundary, and I'll create these toolpaths. I don't have to create, in fact. If I have, I can go here and click on Contour 4. You can see that I already have those boundaries with me, so I'm going to use that. I'll provide an offset of, I don't need an offset. I'll just keep the toolpath outside the boundary and just trim the passes and recalculate the links once again. Right. So we have removed those passes from my toolpath, and I have got an excellent toolpath now, which doesn't do any unnecessary cutting anywhere. So I can now either take the G-code generation and just generate the G-code. Okay, so I've got a Siemens code coming out, which is for the 828 control, right? And once this is also done, I can do the simulation. So I can do a lot of different simulations. So what we're going to do is I'll run the simulation here. Let's go to my settings. In the machine simulation, I'll enable verification so I can see the material simulation, and I will take this into the machine simulation. Remember that we used an AMS MCV 450, so I will see an MCV 450 machine. Okay, so I have the, let me switch off the workpiece. So I have the part here, the tool, of course, I did not define any holder. That's fair enough. And on the visibility, I can actually show my entire machine housing. So that's MCV 450. Go into the access control, I can remove the doors and look at the machining. Okay, let's start. So this is how my machining will start. We can increase the speed. You can see that it has done completely one go, 17 millimeters. And once this is finished, it will then start doing the step up to do the scallops for me. Somebody asked if you have any tool for customizing the post processor. Yes, we have a tool. However, most of the post processors are directly customized by us sitting in India. So you don't need to do all that. We will give you ready to run post processors directly on your machine. You don't need to do anything else. Okay, so more or less we have completed this part. We can keep running the simulation. Once this part has been machined, you can actually go into the part and you can run a deviation analysis between the part and the stock, and it shows us basically you can see these ranges here. You can also go into measure and select a point, and it tells you what is the difference between that particular point and the surface nearest to it. So here it is showing 0.9. I can just go randomly pick a point here. This is 1.32 millimeters. So a lot of material is remaining, and I can, without going out from here, I can start the next process and so on. Okay, so we have we have the part here. So let's switch off the Ys, and I can simply go into my operations here, generate, and say generate a tool sheet. We have again got customizable tool sheet the way you want, generated in Microsoft Excel. I have one of the tool sheets, and I'm going to generate this tool sheet for this part with the process. Sorry, yeah. Sorry, I had my Excel running here, and that's the reason it did not create. So I'm going to close this. Let's run the tool sheet again. So the formats that are supported are Microsoft Excel, a Word format. You could generate it even in HTML format. So there are several formats by which you can generate your setup sheets, and everything of that is customizable. You can see here immediately, you get the part name, who is the project engineer, where is the directory, your project prefix, the date, comment, and you get the processes. You get the tool description. If you have put in the tool description, you get the tool description, tool number, the ID, the cutter diameter, the corner radius, what is the RPM, what is the feed rate, and what is the cutting time for each of this process, along with, you can see this image. That is the reason I had put those dimensions to show to the operator that my origin is right over there, and those are the dimensions that you need to move to go to my origin. Okay, so this is one process, start to end, for a medium part. Let me quickly open another part now. And this is the insert that George showed at the end, and we are going to machine for that particular insert. Okay, let's go to the SplitWorks insert. And this is a reasonably large insert. So you have a part that is approximately 450 by 350 by 200. So it's a pretty large part. Again, here, I'm going to use a template that I stored here. So I have got my template. It's a mold insert template. Just going to drag and drop it out here. And quickly, I will show you a few more strategies on this before we wind up for question and answer. Of course, this is going to take about 15 minutes or so. Okay, so first one, we have, again, a contour roughing, which is an HSR, and geometry is a target. 0.7 is a step, the stock to be left, and step down is 1 millimeter. I'm using a 32R3 bullnose. Let's run the calculation very quickly. Somebody asked whether we generate a mesh. Yes, in a high-speed machining, we do generate very fine mesh at the back end to generate our programs. Okay, that's how most of the 3D systems work. Okay, calculation is almost done. That took a few seconds to calculate. So I have my roughing toolpath. So if I run the simulation in my Solid Verify, okay, that's my part. Let's quickly run it. And this is how my machining will go. Okay. For many of you might not see the simulation because in the webinar kind of an environment, only static images go into the in the internet. So you might see the change only when it runs several slices. So you see these slices. So that's how it's machining my entire part. Remember that I'm using, I'll show you on the geometry, I'm using holder. So the first tool, since it's got a pretty long overhang, it has got an overhang of almost 90 mm. That's like three times the diameter, which is fairly good enough. It can rough out completely, but when I go into the shorter tools, I can't really go into those areas which are pretty deep. Okay, so we are going to see another new machining technique for going into the deep segments. Somebody asked if we need to create a drag and drop templates. We do not provide standard drag and drop templates. The templates need to be created by you. I'll show you at the end how you create the templates. It's like 1 second operation. You create the templates, and the templates get stored in a particular directory. It's visible to you on the sidebar. You can just drag them and drop it on your geometry. Okay, so almost done the simulation. Perfect. So that's done. So this is how my roughed out part looks like. Of course, I know that I need to put a lot of rest roughing operations here. So this is what I have here, my next rest roughing operation. And here I'm using a 16 corner radius 3 bullnose tool. I'm going to pick this and say 0.7 millimeter. Stock, it should only cut anything beyond 0.8 millimeter. And in the passes, we'll have the 0.5 or 0.7 millimeter step down and about 7 millimeter step over, or less, maybe 50%. Okay, we are not using any reference tool here. The link, I would like the step. That's it. I'll just save it. Because this template was already done, it works very well. You can just run the calculation again. Again, here, it's running the updated stock calculation. So it wants to know what the previous roughing has done. And this is generally done only once when you define an operation. Okay, if I again go and modify this operation, it will not run the updated stock because it already knows in its memory what the updated stock is. Okay, stock is calculated. We're now going to move the stock, the part, and everything else into the calculation environment. Again, you can look at the calculation time. We've given a down step 0.7 with a 16 with the updated stock calculation. And that's the real-time calculation time that you're seeing on your screen. Okay, it's almost done. It's trimming the passes to the stock. Adding the lead-ins. And in about 45 seconds, we have already finished the calculation. And because I used the holder, you can see that this region is completely untouched by the tool because it's unable to move into that region. Why? Because this is approximately more than 83. In fact, if I pick these 2 points, so it's about 88 millimeters. And if I look at my tool, tool number 2, it has only 70 millimeters overhang. So it definitely cannot reach this area. So it has left out this area. Fair enough, not a problem. We'll move to the next rest roughing because now I've done with 16. I would now like to go with a 12R1. Again, I've used a holder here, and the tool out of holder is only 50 millimeters. So it's obvious that it's not going to reach several areas. Let's pick the boundary. Let's pick the target first, sorry, 0.7. Okay, and we need to go anywhere beyond 0.8. That's it, passes. Like to go 0.5 millimeter here. Okay, that's it. Let's go to the link. It's all done because this template has already been set. It's pretty simple. Rest on the calculation. Again, now it runs the stock calculation of the operation just above it, which was the operation that we just did. And of course, somebody asked if you can show the template creation. Yes, at the end of the process, I'm going to take all the entire toolpath and I'll show you template creation, both the process as well as the individual toolpath. So you can create templates for both the individual toolpaths and as well as the process itself. That means the entire group of the toolpaths can be sent as one process for templates. So the user, when he applies, let's say we have got a very experienced user and he has created process templates. So the user who's junior to him simply pulls the process templates and applies it to his geometry, and the calculation starts. He doesn't have to really think too much because somebody else has already done the thinking for him. Ilker is asking what kind of options we have for smoothing. Okay, so we have got corner smoothing as well as pass smoothing, as well as the rapid smoothing functions in SolidCAM's high-speed machining. Somebody is asking what PC configuration I'm using. I'm using a mobile workstation. It's a Lenovo P52 with a 48 gigabyte RAM. and it has i7 8th generation processors. We have approximately, I think it's 6 cores. And the main hard drive is an SSD. The secondary hard drive is also an SSD. Somebody is asking, in the previous part, the calculations were faster and the calculations are slower in this part. Well, it has to be, because the earlier part was only 180 by 135 millimeter, whereas this part is 450 by 350 by 200. That's the size, okay? So this is the longest operation, took about a minute. Again, you can see that because of the holder, it did not still clear areas here. It did not clear the area here because it was coming close to the part. So several areas are left out. It's unable to clear. Well, we don't have to worry. What we are now going to do is, I have put another rest roughing toolpath, and this time I'm using a 10 ball nose, okay? I have got a very specific reason, and you can see that I am not using any holder to this. Okay, if I go into my tool, it's a 10 simple ball nose, dimensions are unknown. And if I go into the, if I show you visually the tool, this tool doesn't have this tool doesn't have any holder attached to it. So this tool is going to go into all those areas which were left out by the earlier tool, because it doesn't have holder, so it can practically go everywhere. Okay, so I'll accept this. Let's go to the passes. Everything is the same. I don't need to do anything. Only thing is the step down and step over, which is pretty good, 0.5 and 2 millimeters. Somebody asked why I do save and then I go on calculate. Well, it's my habit that I close this window so I can see what is happening. Okay, that's the only reason. Otherwise, there's no distinct advantage. So let me calculate this operation. Again, stock being calculated of the previous operation. And once the stock is calculated, it'll pass on the stock to my subsequent operation and we'll do it. And once this operation is calculated, I will show you a very, very interesting feature. The updated stock is calculated and now it will create the passes for me. Remember, now it's going, the 10 diameter tool is really going to get a lot of areas to cut, because 16 diameter did not go into several areas. For two reasons: one, the length of the tool itself, and the other one is the geometry, the diameter itself. Then we had 12 diameter. Again, it has got its own reasons for not entering diameter as well as a length limitation. So my 10 diameter ball nose tool is actually going to get a lot of area, especially around this vertical walls here, which it needs to tackle. Okay. Somebody asked a question. I'm also going to take questions also when it's calculating. Since I've not defined the outer, the tool length outside the holder, how will it machine? Okay, because we have not defined. Well, that's a very good question, and that is one of the features that I'm going to do. So you can see that it has got plenty of areas that was not taken care by my earlier tools, right? So we have machined, it has machined into every area. Obviously, this length here is 88, 89 millimeters, and we cannot have a 10 diameter ball nose tool sticking out of the holder by 90 millimeters. We are going to create either a very bad surface, or the tool is just going to disintegrate. It'll break, because L/D ratio of 9 is unheard of in these kind of machining environments, especially with such thin tools. So what I'm going to do is I'm going to take advantage of my 5-axis machine. Okay, so I'm going to right click on my operation. I've defined, by the way, a DMU 50 here, which is a 5-axis machine. I've put the part on the 5-axis machine, and I will just take this part and go to conversion 3 to 5, and I'll say convert this HSM toolpath to 5-axis. In conversion, again, we have got two options. Conversion, which has got a lot of parameters, but user gets great control. And then we have auto tilt, where user really doesn't have any choice. The software will handle everything else for him. So I'm going to use the first one, which is the user has got a great control on. And in the source operation, you can see that it's showing me the rest roughing operation just above it. So I'll pick that operation, which is my source. The tolerance and arc approximation tolerance is going to be picked up from the earlier operation, so I'm not going to change that. The links are also not going to be touched because it's going to use the source links. The tool, however, is going to be a completely different tool. What I'm going to do here is I'm going to check if I have got a tool with a holder. I don't, so I make a copy of it. And out of holder, I'm going to say 40 millimeters, and I'll define the holder. Okay, so I'll pick the holder here, which is a shrink fit 10 diameter short holder here. Okay, so this is how the tool will look like. With the tool and the holder together, I'll apply it. In the tool axis, I'm going to use tilt to Z axis. Okay, simple. 0 and 0. That means if the holder doesn't make any kind of a collision, just stick to your 3-axis, else tilt. Simple as that. Maintain the tilt, and in the gouge check, I will say only check for the holder and the arbor. I don't need to check for this because this is already checked during my calculation in 3-axis. And in the check surface, I don't want to select all the surfaces. I don't want to get into that. So I will use an STL file. I don't have any, so I'll define a new STL file, and I'll browse for my STL file. And under HSM, I get this target HSM, which is the STL file of my target. Select it, and let's say 5x convert is my name of that file. I'll accept it. Okay, and this is the clearance. It will clear the holder by 2 millimeters, the arbor by 0.5 with reference to your target. So I'll save this. And like my usual, I'll hit the calculate button. So what it is now doing is, it is doing the loading of the original toolpath. And once it loads the complete toolpath, it's only going to run the collision checks. Pretty quick. You can see a rest roughing toolpath, which was purely a 3-axis toolpath, being converted into full 5-axis. Okay. Oh, we have a problem here. You can see that it pulled out this toolpath and did some mess. Okay. That's because I forgot a thing here, which I should not have. If I go into my tool axis control, or in the gouge check, I said retract along the tool axis whenever you find collisions. It's not going to be retraction, it's going to be tilting of the tool, and we're going to use a 3 to 5-axis conversion. Save. And now I hit the calculate button, so it's not going to load any tool paths. It's just going to run the collision check for me. Somebody is asking how to check the collision in rest machining. You don't have to do any collision checks because the collision checks are already performed when the calculation happens in the software. But if you want, you could always simulate the toolpaths and do a comparison between the stock that it has cut versus the part that it is there, the part. Right, so you can see now the toolpath looks nice, but you don't see any 5-axis movement. So for that, we'll have to go to the simulation. And I'm going to run the simulation here in my solid verified, in my host CAD. Okay, so let's go to the front view. So it's doing this area. You can see at the moment, it's only doing 3-axis, okay? So let's, once it comes close, once the holder comes close within that striking distance, it will tilt itself. You can see now SolidCAM has tilted the tool. And now it's going to perform the rest roughing in 5-axis. Okay, now it's going to perform this rest roughing in 5-axis. By clearing the tool away from, or the holder away from the part surface. It's going to maintain the clearances that I've asked it to maintain, 2 mm for holder, 0.5 mm for the arbor. So it's going to maintain that and machine every deep area in my part using 5-axis. Okay, so that's a great advantage of using 5-axis for mold making. You can use short tools and you can go really deep into the mold without having to worry about tool length. Okay, as long as your holder can reach, by the way. Okay, so what we did just now was to create a 3-axis rest roughing toolpath, and just with a click of a button, we converted that toolpath from 3-axis to 5-axis straight away. Areas where it doesn't need, it will keep the toolpath as 3-axis. Areas where it needs to tilt, it will convert only those areas to 5-axis. Somebody is asking me, okay, that was about this. Somebody is asking me if we have got option to define collision for clamps and other things. Of course, in each of our roughing and finishing process, we have got, if you go into the geometry, we have got fixture definition, where you can define fixture by the faces, part, or you could simply make sketch and say that sketch is your fixture. It will avoid the fixture by not getting into that area at all. You can provide offsets. You can say, I've defined a fixture, stay away from this fixture by 2 mm. Okay, so you can even do that. So that's possible. Right, in the same way, I'm now going to calculate my toolpath with just using a tool without holder for constant Z. Again, here I'm using 45 degrees to 90 degrees. That's the slope angle and a bidirectional cutting. Let's save this. And I'll go to the linear, edit the linear. Again, here I'm going to use applied multiple. I'm again taking a 10 diameter without any holder because I would like to use the 5-axis, and 0.4 step over, 45 degrees. And here I'm saying 0.005 to 47. So I'm asking SolidCAM not to cut absolute flat areas because this part is huge. I do not want to waste my time taking a ball nose tool on the areas where I can do it easily with a bull nose tool or a flattened mill. So I would want it to avoid all those areas. So I've given a very small increment in my angle. Save this also. And then my rest machining. Again, big advantage because I'm using a 6 diameter. Imagine using a 6 diameter in this area, which has got approximately a depth of almost 90 millimeters. Okay, this is where 5-axis will come handy. My earlier reference tool is diameter 10 with corner radius 5. And here I'm using 0.3 millimeter step over and step down with a 45-degree slope. That is the differentiation between steep and shallow area, and linear machining for shallow area, constant Z for steep areas. So we have got bidirectional for shallow areas and climb machining for steep areas. That's it. And the last one is the horizontal area machining, which I am going to use for machining all the flat areas. So I will take this toolpath, take everything and put it for calculation. Okay, so like the previous part that I showed you, when we put a lot of operations to calculate, they are calculated parallelly. For example, the rest machining is now working, linear is almost done, the constant Z machining is happening, the flat area machining is already finished. So the only area now remaining is a constant Z and the rest machining. Those two are being calculated. Constant Z is also done. Now it's going to it's only calculating the rest machining toolpath. So we can now apply the same 5-axis conversion that we did also to constant Z, also to linear, and also to my rest machining. I will quickly apply it only for the rest machining just to show you how nicely it does with the short tool. In the meanwhile, please keep your questions coming. Somebody is asking me if this is turbo HSM. No, this is our generic HSM, what I've shown you. Turbo HSM would have been much, much faster. Okay, rest machining is already finished. It's collating the toolpaths. You can also look at the calculation speed of these paths. These are really big paths, okay? So the calculation speed is running into seconds when it is doing the calculation. Okay, so what we have here is my HSM. the constant Z, you can see it has left out all those areas where horizontal or the shallow areas. It's only machining the steep areas. After that, I have got the linear here, which is doing all the shallow areas. And then I've got my flat, which is only machining absolutely flat areas with a bullnose tool. I've machined with the bullnose tool because it just doesn't make sense to use ball nose on these large surfaces. Okay. And I'll show you a couple of other features also before we wind up. This is the rest machining. You can see constant Z in the steep areas, follow the surface in shallow. Again, constant Z in steep areas, follow surface in shallow. Let's open the linear machining. And you can see that I've got passes here on the edge, which I don't like. Okay, so I can do two things. I can start my toolpath much lower as a start point, or I'm going to show you another feature where I'll make a sketch here on this plane. Okay, and I'll simply make a rectangle here, and we will edit this toolpath with this side. So I'm going to use a boundary, and I'll pick this particular boundary here. So you can see I'm going now in my, this is the exit plane. Take that, keep the toolpath outside the boundary, calculate the trims. Okay, so it's just running the relinking now. It's trimmed the toolpath and running the relinks. Okay, you can see that I've chopped that area. I don't get that area anymore. So I've just now this area to work with. Now let's go to our rest machining and do the same conversion. So I'll convert HSM to Sync 5X. My source operation is the rest machining, and I'll go to the tool. I don't have a tool here, so I'm going to make a copy of this tool, and this is 60 millimeter, and outside holder is only 25 millimeter, and I'm going to use, sorry, this is 20, and my cutting length is 14 to flute, and in my holder I will use again a shrink fit holder of diameter 6, 50, that's it. Right, so maintain tilt and a gouge check. Just check for the holder and the arbor. I don't need to check anything else. And the check surface that it needs to check against is the same STL file that was used earlier. I don't need to do anything else. I just say tilt the tool, convert 3x to 5x. That's it. I'll just save this toolpath and run the calculation here. Again, it's loading the toolpath. And once the toolpath is loaded, it'll just run the conversion from 3 to 5, and we should get a very nice 5-axis toolpath out of a 3-axis rest machining toolpath. Somebody asked, how will feature recognition work? Well, in SolidCAM, we have got 3 types of feature recognitions. One is a hold recognition, the other one is a pocket recognition, and the third one is a chamfer recognition. Of course, we will not use chamfer recognition for molds, because in molds we need sharp edges. Chamfer is more used for aerospace parts where you need to do edge breaking of the part once the entire cycle is done. So we'll use chamfer recognition for that. For holes and pockets, we will use if the part has got too many holes to be drilled with different directions, different type, different size. We will use hole recognition for that. And if you have got a lot of pockets, then we can use pockets also for pocket recognition as the AFRM, or the feature recognition and machining cycle. Okay, so we have the part here. Let's run the simulation. Okay, it's running the linear first. Okay, let's finish that quickly because I'm more interested in this region here. Okay, you can see that moment it comes into this region here, where it's going to find a collision between the holder itself and the part, you can see it tilts automatically. It's tilted itself, and this is how the machining will happen. Okay, again here there's no collision, so it's going simply in 3-axis. Okay, and then again tilting. Then it comes here, which is our area of interest. Let's increase the speed. And as it comes close, okay, what I'm going to do is go into the front and zoom into this area. As it comes close, you will start seeing that it starts tilting itself. That's it. And how will this look on the machine? Let's take this and edit this and just check if my angle pairs are right. Need to go into the second angle pair. I'll just save it. Now run the simulation with the machine. Oops, I'm so sorry. Should not have done that. It was with the stock. I don't want to see the stock. Yes, please. So I have a DMU 50 machine loaded up here with the part, and let's show the workpiece. The workpiece here, tool path, can start simulating it. So this is how it will move. And let's go to the move list. Let's drag it down so that we go into the area of our interest. Let's increase. So as long as there is no real threat to the holder, it continues in 3-axis. And the moment there's a threat to the holder, you can see that it starts moving in 5-axis. Okay, so the moment there's a threat, immediately, if it's come pretty close, it starts tilting itself to avoid any kind of collisions with the holder and the spindle. Okay, so that's how 5-axis works. And if I generate the G code of this for my, oops, just this, sorry, it's not for this. Okay, again here I can apply the same functionalities that I applied. I can create my setup sheets, I can create G codes, I can simulate on the machine, I can do regular simulation. Everything is available. And if somebody asked me, can you show me the turbo HSR operation? Yes, of course, I can show you the turbo 3D HSM. Let's take linear machining, and I'll pick the tool, let's say diameter 10, and somebody wanted to see the speed of calculation of the turbo HSM. And if I go into the passes, let's say this is 0.5 millimeter, and I'm going to go at 45 degrees. That's it. Let's save it. It's a zigzag operation. Okay, so let's calculate this operation. So if you want to see the calculation speed of turbo HSM, remember, part is 450 by 350 by 200. So that's the size here, and it has calculated the tool path in 13 seconds. So that's the speed at which we calculate the tool paths. So some people say we have good editing, which actually you don't need, because when you have good calculation speeds, you can run several iterations even before somebody does editing of 2 or 3 different tool paths. Okay, so you can run a lot of iterations within a minute. You can do, for example, if it's going to take 13 seconds, you can run an iteration of almost 4 to 5 times within the 13 minutes to get the best possible tool path that you're looking for. Sanjeev is asking why we can't use iMachining, because I just showed you iMachining for small part. Why we can't use iMachining for, let's say, a part like this. Okay, Sanjeev, the problem here is not iMachining. iMachining can still handle it. The problem is going to be the comparison between the part size and the cutter diameter. Since iMachining works only with solid carbide end mills, we have to understand that solid carbide end mills end at diameter 16. You also have 20, 32 all, but they are very, very expensive tools. Okay, so economical end mills stop at diameter 16, and if I use diameter 16 for, let's say, this part, I'm actually going to increase my machining time, even though I've put iMachining. Okay, so not every part needs iMachining. So a part up to, let's say, 250 millimeter or 300 millimeter can be an ideal candidate for iMachining roughing. If it goes beyond that, then it's a user's judgment call. But parts like these, I would not suggest to use iMachining. You can go with the turbo or the generic 3D roughing here, which are much faster and give you an excellent result, okay, for machining. Right? If there are no more questions, we have actually come to an end to it. We have almost exceeded 2 hours and 10 minutes. It was really an excellent and informative webinar, I hope, for all of you. I have got 2 announcements to make. For people who want to evaluate SolidCAM, please go to solidcam.com, download a fully functional version of SolidCAM for 2020 SP1 for 60 days. It allows you to use for 60 days with all the post processes that come standard with the product. For people who would like to evaluate electrode works, split works, and mold works, well, please go to this website. It's rnbusa.com. Okay, it's rnbusa.com. The mail that will go to you, the thank you email that goes to you at the end of the webinar will include this operation. So you can see that they have got products for split works, mold works, and also electrode works, and you can evaluate these products for free for 30 days, either of these products. So you can evaluate the split works for 30 days, you can evaluate electrode works for 30 days, and also mold works for 30 days. Okay, so you can evaluate, find the best possible product for you. Get in touch with us, we can train you. Very important. That's most important here. Downloading a product is easy, but getting training is the most difficult part. Get in touch with us. The email will also include information on which email ID you need to get in touch with us for the training. We have got batches going on every day. Join one of them, and we will take care of your training from scratch till you are an expert. That's our guarantee for you. Right. Thank you very much for listening to us for such a long time, more than 120 minutes. It's a long session, and we hope to see you again probably next week with one of another very interesting webinar. And till then, please take care, stay safe. Bye-bye.